Now we will solve the last question in this method. And by looking closely to the recurrence relation, it says an, you take the previous value an minus 1 and you add 3n squared. So for a1, if n is 1, remember that you substitute 1 for n. So it will be 3 times 1 square. For a2, it will be 3, 2 square. For a3, 3 multiplied by 3 square. So first we need to find a1, which is equal to a0 plus 3 multiplied by 1 square. Now, since this equation depends only on a0, so we will leave it as it is. Now for a2, it is equal to a1 plus 3 multiplied by 2 square. We have already found the equation for a1. Simply substitute it here, and it will be equal to a0 plus 3 times 1 square plus 3 times 2 square. And again, don't try to find the final answer for this expression, and don't find the final answer for this expression, because if you find the final answer for these expressions, you are hiding the operations in between. So you will hide that 3 is multiplied by 1 square, 3 is multiplied by 2 square. So just leave it, because you need to discover the pattern for the next iterations. Now let's go for a3. Now a3 is equal to a2 plus 3 multiplied by 3 square. This is the value for a2, so you need to substitute it here. And this is going to be equal to a0 plus 3 multiplied by 1 square plus 3 multiplied by 2 square and 3 multiplied by 3 square. And maybe we should go for one more, which is a4 equal to a3 plus 3 multiplied by 4 square. Again, this is the equation for a3. Then you need to substitute it here. So it's equal to a0 plus 3 times 1 square plus 3 times 2 square plus 3 times 3 square. And we have one term which is coming from this equation, which is 3 times 4 square. Now we have the expression that is number of terms is enough to explain itself. We can say that by guessing what will be the equation for an. See, it starts with a0. For a4, it starts with a0. a3 starts with a0. a2, so for an also will start from a0. Now for the remaining terms, this is a summation. But if you notice inside, we have a 3. So a 3 is common. So we will take a 3 outside. And inside, we will end up with 1 square, 2 square, 3 square, 4 square. We continue. What do you think the last term will be? If this is 4, the last one is 4 square. If this is a 3, the last one is a 3 square. So if it is n, then the last one will be n square. And this is equal to a0 plus a 3 multiplied by summation. Now we will designate the variable inside that is changing by k and starts from 1 and it ends up to n, and inside we will have I raised to power 2. a0 is given at the beginning is 0. See, a0 is 0. So we will substitute for 0, 3. Now, the equation for I square, if you recall, it will be n multiplied by n plus 1 by an odd number, which is 2n plus 1 over 6. So we can divide both sides by 3 And the equation that we will have for an is equal to be equal n plus 1, 2n plus 1 over 2. And this is the final answer for our recurrence relation. So this is a solution for the recurrence relation. This method is called forward chaining because we start from the beginning forward. So we start from the first term, initial value, we go to the next one, we go to the next one, and etc.